Hi friends, this is Dr. G. Srinivasa Gupta, Professor from Department of Mechanical Engineering of VJEC Institute of Engineering Technology. Today we are going to discuss numerical problems on balancing of rotating masses using graphical approach. This is the part of Dynamics of Machinery course. Previous lecture we have seen analytical approach, how to find balancing mass or whether the given masses with the rotating shaft are under balancing or not, we have seen. Now similar problem we can attempt using graphical approach. As you know that static and dynamic balancing of rotating masses requires balancing of all the algebraic sum of forces as well as algebraic sum of couples or moments due to these forces should be balanced. If it in case of dynamic balancing, in case of static balancing, algebraic sum of all the forces need to be balanced. That we have seen. This is the dynamic balancing case. Force balance, couple balance required to be satisfied. If there is any unbalanced force or couple which need to be balanced, then we need to add additional mass, and depends on the balancing requirement, force or couple, we need to look into the planes in which the mass need to be added with the corresponding radius of rotation. For this we have seen various numerical problems on analytical approach, using analytical approach. So this is the for previous lecture, those let us just scroll out all these problems and similar problems how we can attempt using graphical approach we are going to discuss today. Okay, if it is only single mass, single rotating mass, then we need not worry about, because as balancing of forces required, algebraic sum of M R product must be 0. So obviously if there is single mass, then it should be balanced with corresponding mass and radius product. So we can directly do this problem without any whether graphical approach or analytical approach. There is no point of talking about graphical approach for this simple problem. Okay. Now coming to two rotating masses. Okay. In this case, this is the two masses rotate in the plane, single plane only. So 5 kg one mass, 100 mm radius, it is rotating with an angle of at that instant 0 degrees angle, and second one is 8 kg. That mass is located at a radius of 150 mm from the axis of rotation of the shaft. Its orientation is 90 degrees. In this case, graphical approach, if we want to use, this is a numerical approach, MR. As you know that in numerical approach, all the horizontal components of these forces must be balanced, and vertical components also need to be balanced, or the resultant need to be balanced. For that we are taking a mass which is kept at required radius. In this problem, radius, at that radius how much mass you need to put such that it is maintaining the balance. That's why we got resultant of given masses with the radius of rotation is, we got in this problem 1300 newtons. Okay, then that resultant, Newton meter actually, that resultant must be equal to the balancing mass put at radius RB, that is equal to MB. So MB can be found because RB is given at 200 mm radius, what is the mass required to be balanced. This we have seen this problem, and angle of at with what orientation this balancing mass need to be placed, then that orientation also we can find using analytical approach. Theta is equal to tan inverse algebraic sum of all vertical components of forces by horizontal component forces. So we will get the theta, that is the resultant of given forces, then exactly opposite direction, that is 180 plus that orientation, that force opposite direction we need to show, as we have seen this problem. Then suppose same problem using graphical approach, then you need to draw MR vector diagram. Okay, MR polygon we can say. In this case, you need to first of all calculate MR. Here MR is 500 per first mass, and second mass MR is 1200. Then what you need to do is, because this is units are kg, mm or kg meter, so you need to take scale conveniently. Suppose 100 kg meter, this is 500 mm actually, kg mm. So 100 kg mm is 1 centimeter on my scale. Let us say 1 centimeter equal to 100 kg mm. Then obviously centimeter, this one. Then obviously how much you need to take a length of the scale on your drawing is, because this is 500 kg mm, so you need to take 5 centimeter length. So mass 1, okay, 5 kg mass, let us say vector mass 1, vector diagram you draw, mass 1, because it is what is the orientation? 0 angle. So I am taking, it is horizontal, this is the 5 centimeter line. Okay, keep in mind that the scale you have taken, because at the end whatever result and balance force required, that you need to apply, reapply the scale and get that value. Okay, so then this is tail end of this vector and head of this vector of first mass, that is MR value. Then second one 1200 kg mm, so 12 centimeter line you have to draw with the orientation of 90 degrees. So the head end of this first vector, you have to start with tail end of second vector. This length you have to draw 12 centimeters as per scale. Then it should form closed polygon, then only it is maintaining balance, because these two masses only given. So obviously third one, that means balancing mass required, that corresponding MB/RB value is giving this closed side of the polygon. This is triangle, basically we are getting closed side. So measure this value, measure this length, and you reapply the scale. Then that is equal to, so this let us say x is measured, and with centimeters you will get x into 100 we have taken scale. This is equal to your MB/RB, right? Then obviously you can find out, because at a given radius what is the mass required to be attached. Then RB is given in the problem statement, x you found from this polygon construction, and this is 100 scale, so MB you can find. Once you get the MB, once you get this MB, then orientation of this mass with respect to the reference axis is, you can see that what is the orientation, measure this angle theta b, let us say this theta b is corresponding orientation. This is force balancing. Suppose couple balance, this is single mass, two masses rotating in single plane, so there is no point of talking about couple, there is no couple exist. Suppose the problem which arises couple balancing, we will see the masses, what is that case basically? When different masses are rotating different planes, then to balance them, then it is couple moment or couple also arising due to the rotating masses corresponding forces. Okay, so for that case we will see such problem. Okay, okay, we are going to discuss now in actual polygon method. Okay, like this any problem you can attempt. If it is force balance only for force polygon you need to draw, that is enough. If it is couple as well as force, that is dynamic balancing case, you need to draw couple polygon as well as force polygon. Okay, what is basically polygon means? For rotating masses in one plane it is easy, single force vectors you are going to take and draw the polygon. Okay, that is each mass produces a vector MR. These vectors are drawn to scale at a given angles, that only we did just now. The closing side of the polygon gives balancing mass, that we have done. Okay, you can attempt this problem. MR polygon, that is 4 masses rotate in same plane, single plane. So 4 masses here. So suppose in this case you calculate MR values. Okay, MR values shown here. Okay, then this is 400 kg mm. 900 second mass 6 kg, that is 900 kg and third mass is 600 kg corresponding force of that mass. Okay, then for vector diagram, MR vector diagram, you choose convenient scale. Here 1 centimeter equal to 100 kg if you choose, that is convenient for these values of MR values of corresponding masses. Then 400 kg 4 centimeter line you have to draw. So first mass you see the angle 0 degrees orientation, second 90, third 210. So I am going to draw this. First mass you take and 4 centimeters is the drawing vector. Let us name that AB vector. Okay, horizontal only, 0 inclination. So AB vector. I will use small letters in the vector diagram. Of course, I have mentioned vector AB, capital A. Okay, same let us use AB vector. Okay, this is AB vector. This length is 4 centimeters. Orientation is 0 degrees angle. Second mass 9 centimeters you have to take. MR value of second mass is 900 kg So 9 centimeter as per our scale 1:100. 1 centimeter equal to 100 kg Then it is 90 degrees orientation, 9 centimeter line you need to draw. Second mass 90. This must be vertical. Vertical means 90 degrees orientation with the reference line. So this is BC we have named. Okay, BC. Then third one is 6 centimeters line we need to draw with the orientation of 210. So from C it starts and CD orientation is 210. How you can make orientation 210? Draw reference line. Okay, then it is if you say this line reference line extended 180. 210 means additional 30. Okay, this is the orientation 30 I have taken. So this is the orientation of third 6 centimeter line you have to draw. This is CD. Obviously, to maintain balancing, then balancing mass required, how do we get? This closing side, DA side, DA. DA is the basically resultant of all these forces, resultant. Okay, so DA, you measure this length, resultant of all these forces. Okay, you measure this length and DA and apply the scale. That's much DA you got here. If you plot draw this polygon diagram, then vector polygon diagram, MR diagram, then you are going to get DA is 5.5 centimeters. Okay, so then orientation also you can see if you want. So DA vector, it is resultant. From here you are going to draw here, then resultant you are getting in this direction. Okay, this is the resultant. From here to here the resultant. Then opposite direction you have to keep the mass exactly opposite. Anyhow, this angle orientation, let us say, this measure this one. Okay, so then this balancing resultant you can say 550 kg you got. Then how do you make it? So this is magnitude. So our balancing mass must be equal to kept at magnitude must be 550 kg Then MB you can calculate MB because RB is given 140. Here you can see this is a 140 radius. How much mass required? Mass is not given in this problem. So MB you can find out. MB you got 3.93 kg. Then what is the direction? So DA is the resultant you have seen. Opposite to that exactly. So opposite direction you can here diagram I have shown. This is the resultant and exactly opposite direction. Okay, orientation is same theta and opposite direction you keep because DA vector is this one, this direction, resultant DA. So from the soft axis exactly in opposite direction you need to keep this your balancing mass. Orientation is same, whatever orientation this is. Understand or not? So this is about okay the balancing mass required. Okay, that is equal to closing side magnitude and orientation is exactly opposite. Okay, so this is about this problem and we will also see MR. This is single plane, all the masses are rotating. In case of masses are rotating in different planes, then how do you approach? That we will see. Okay, basically dynamic balance concept, that one. So here for rotating masses in different planes, two conditions must be satisfied, as you know, force balance, couple balance. Then so MR polygon we need to draw, as well as MRL. MRL means couple. How do you calculate? Force into distance from the reference plane the force is acting. Okay, suppose here two forces, this is one plane, this is another plane, so some force is here. Okay, what is the this is the m or distance. Force is, what is this force? M r omega square. So what is the moment of this force about this plane? Then this length will come into the picture. Okay, m r omega square into length. So omega square is common for all, as we mentioned previously also. Then MRL. So MR polygon, MRL polygon. Both the polygons need to be constructed to check the balancing of these masses located in different planes. Okay. So any unknown quantity of given set of masses rotating, that unknown quantity we can find. Okay, so balancing mass and angular position using graphical method we can see for the given values. So here four masses, one mass is not value is not mentioned. So and radius of rotations for all each mass is given, and plane of distance from A is taken reference plane, first one. First 5 kg mass wherever located, that is taken as reference plane. For this problem, if you just different planes and orientations also different. So let me just draw the sketch. This is 0 degrees orientation. In this plane it is lying. Okay, plane, let me draw. This is the plane. Okay, in this plane 0 orientation. 0 orientation means in this direction, and that is 5 kg. I will write M1 this one, and radius is at the radius where it is located. Okay, from this reference point. And second one is 6 kg 150. This is 200 mm radius. Second one is 150 kg. This orientation is 0. Second one 90 degrees orientation, but the mass is 150. Mass is 6 kg and radius of rotation is 150. This is M2. Okay, and the third one is 180. 180 means exactly opposite to this. Okay, 180. Okay, so this is third one, M3. And fourth one, radius of rotation given, and also orientation is not given, mass is not given. So how much fourth one, what is this orientation? M4. You need to find. Radius of rotation only given, but orientation, theta also, you don't know. Okay, these things you need to find. For this, what you need to do, you can make the table of MR and MRL values of all these with unknown, whatever it is. Here, see here, MRL and MR if you draw. Only three masses we know. All these, okay, because M we don't know and theta we don't know. M we don't know. That's why first three masses you calculate MR and MRL from reference plane distances. First mass 0 distance, because in that plane only, with refer to that plane only, we are taking moments of forces lying in the other plane due to masses. Is it okay? So this is first force MR, M1, R1. Okay, and in this plane only we have this M2. Okay, how these are located also, we plane from distance, reference plane first one, and second one is 6 kg, and third one. Okay, fourth mass, last mass, whether you need to keep it in which plane also you need to find actually. That fourth mass is not given, that should be balanced. That's why first three are taken, which is okay, in different planes, let us say, but we don't know distance. Is it given plane distance from A? Yeah, planes also. These four masses, first mass is one plane, second mass is another plane, third mass 8 kg is in another plane, and fourth mass is in different plane. Means all the forces acting its own individual planes. No force is acting in single plane. Okay, what I mean to say, first force is this plane and second force another plane which is lying at a distance. Okay, sorry, which is lying at a distance of, what is the distance given? 300. Here to here 300, second mass. Okay, in this problem. All the masses are not in single plane as per problem. Okay, and third we have another plane, third mass, which is located at 600 from reference plane. This is 600. Okay, I think you are able to understand. Fourth one, which plane, and okay, what is the distance we need to find. This is the basic problem here. This is not all the masses lying in the single plane. Okay, then coming to the problem, always whichever masses are given, for that we can calculate MR and MRL, and unknown quantity we will see how to find. First we need to draw MRL polygon first, because MRL values of first three masses we know from reference plane, first plane. Okay, then MRL polygon we need to construct. So first one MRL value is 0. Okay, first one. Second one is MRL value 2,70,000. So scale 1 lakh is 1 centimeter scale. If you take, then obviously you will get the length of the second MRL value is 2.7 centimeters. First one is 0. Second one is 2.7 centimeters. Draw the line 2.7 centimeters. Okay, orientation is 90 degrees. Okay, orientation is, I will start here. Second one, 2.7 centimeters, 90 degrees orientation, vertical line. Okay, vertical. Okay, with magnitude MRL, how much? 2.7. Third one is 180 degrees orientation with refer to reference line. This is my reference line. First one is 0, magnitude also 0, MRL. Second one is this one, 2.7. Third one is 4.8, located at 180. Inclination. So 180 is this one. So 4.8 from starting from second MRL vector. Okay, second force MRL vector head to tail. This is magnitude is 4.8. Okay, because it is given 180. So that's why this is 180. Okay, you can understand from reference anti-clockwise direction our angle. So 4.8 from here, 4.8 centimeters. Then how do you get third one? That is unknown mass MRL. That you need to, as usual, you need to join the closing side of polygon. This is the closing side of polygon. So this is the fourth one required to maintain the balance of all the couples. So what is the orientation you want? Orientation you can see. This orientation is how much? This is 90 and plus something, 90 plus something orientation. And magnitude, measure this length. Okay, unknown MRL vector length. Here you are going to get unknown MRL vector length is 5.5 centimeters. This is 5.5. Once you draw as per scale and measure the final closing side length, you will get 5.5 centimeters. That is our MRL, unknown M, and R is given as how much given? R is 200, and so L is 900. That is also given. So MRL is 5.5 centimeter we get. If we apply square, then into 1 lakh. Okay, 1 lakh is the scale we have taken. So 1 lakh. So then 5 lakh 50,000 you are going to get MRL, kg mm. Okay, right? It is not kg mm, MRL. So kg mm square. Are you able to understand as per? Okay, then this is equal to MRL. You know R and L for the unknown mass. In the last row it is written in that table, given table. So M you can find, because it is 5,50,000 by R value and M value. So you can use substitute. You will get unknown M is, okay, this M is you are going to get 3.05 kg. 3.05 kg. This is unknown mass. Okay, this is the MRL polygon is going to give. Now MR polygon, because always such type of problems we need to start with the MRL polygon. Then only we can get the unknown quantity of mass. Okay, orientation suppose unknown. You can mass is you know. Then also you will find orientation by measuring from the polygon diagram. If orientation also you can measure, because orientation, is it given? Orientation is also not given. Mass as well as orientation you will get from the couple polygon. Once you have mass and orientation, obviously now you can calculate this MR values of all these four, and you can draw the couple polygon, force polygon. Then you can see that whether it is going to satisfy the balancing condition or not. Here suppose MR, okay, this is MR polygon. Let us see, this one you got, okay, MB is 3.05, okay. So here for drawing force polygon, you need to choose different scale. That same scale is not fitting, then conveniently not fitted, so you need to choose different scale. 1 centimeter equal to 200 MR. So then you MR values you have, so you take the scale and draw the MR diagram. Then once you draw the MR diagram, okay, from MR diagram you can, this is the different problem actually, okay. This one is what is the balancing mass required, you have to find in this problem. So draw MR polygon. Previous one you can draw MR polygon and you can construct okay, same thing and verify also. Then here you can okay, draw MR polygon for this masses, and radius of rotation is this one, this problem, radius, okay, for this problem only all the forces are mentioned, and you need to draw MR polygon. So for first force 200 scale, 1 centimeter equal to 200 kg mm we have taken. Then for that you need to draw 5 centimeter line, 0 degree orientation, 5 centimeter line. This is MR polygon. So 5 centimeter, and this is for mass, first mass, MR, M1, R1, let us say, okay, with the scale. Then second one is 4.5 centimeters. Orientation is, you know that, 90 degrees. Okay, 90 degrees orientation, you can draw second one. Okay, so this is 4.5 centimeters. Then third one is 4 centimeters, 180. 4 centimeters, 180. This is force polygon, MR polygon. Okay, then you know that this tail end and head end, third one. Fourth one is closing side, obviously it is going to go whatever way it is going. Then you can see that you are going to get magnitude of fourth one is 3.05, okay, 3.05. Then it is you are going to get, so apply the scale, 3.05 into 200, okay, this 3.05 we are getting, once you apply scale, okay, into 200. Then this is the value of MBRB, is it or not in this problem, MBRB, okay, 3.05 into 200 scale you have taken. So this is the MBRB. Then MB you want, you can find, MB is, okay, 3.05. So how much you got MB here in previous case you have attempted this problem, MB is here, MB is 3.05. So that is verification. Okay, are you able to understand? This is verification for previous problem. Once you know MB, then draw the force polygon and check whether you are going to get correct. That means your previous value is correct or not. You can check by drawing force polygon. Okay, so direction also, as I mentioned, you can see that what is the angle. Okay, the force, fourth one, we can check it and measure it from the force polygon, and we can mention that angle. That is, you are going to get 310 degrees angle direction. Okay, by measuring from force polygon. These are the values. I think you are able to understand how to construct MRL and MR diagram for finding unknown quantities of any mass or orientation. Okay, whatever quantity is gap maintained in the given tabular data, that you need to find by constructing MRL polygon and MR polygon. Generally we used to construct MRL polygon first. From that we can easily find mass. Then second MR polygon we can check the whether it is correct or not, we can checking part we can do that from the force polygon, that is MR polygon. This is about this is the easiest way of doing, and time also you can save a lot of in the exams basically, because in analytical approach you have to take all the horizontal component forces, vertical components in each plane, and you have to solve those equations, and there is a lot of chances to make mistakes. But here also chances, if you are not using proper instruments and orientations, if you do any mistake in measuring orientation of any vector MR or MRL vector of any mass, then it becomes wrong. Okay, so but overall time can be saved using graphical approach, which is very easy to find. Almost half of the time you can save if you use graphical approach. Any for a given problem, any approach you can attempt, whichever feel you convenient, of course. Okay, with this I am concluding this lecture here. In coming lectures, we are also going to see balancing of reciprocity masses apart from rotating masses. Okay, thank you one and all.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.